Okay, so we're ready to define for ourselves a new thermodynamic quantity called enthalpy. We're going to look at definitions and we're going to look at what are called thermochemical equations in this part. So we'll kind of divide this up into two sections. Okay, so this is basically the definition of enthalpy. The heat evolved in a chemical reaction under constant pressure environments. Okay, this is really how it's defined. This is the mathematical definition of enthalpy. It is internal energy plus pressure times volume. That's its definition. That's its symbol, an H. H is used for enthalpy. H and heat, they kind of go together. Enthalpy and heat go together, so we have this H as abbreviation. Notice it's a capital H, so we see that it's a state function. Okay? But we can't any more than determine the total amount of internal energy in something. We can't determine the total amount of H in something. So we will never talk about or put a measurement value for H down ever. But what we can do is we can measure delta H's, because that is what we're really going to be able to measure and quantify, how it changes. Now, since it's a state function, it would be true that delta H is H final minus H initial. That would be true. But we can't know H final and we can't know H initial. So we're going to have to learn ways to determine delta H in a different way. We can't do it final minus initial for a system. Okay, like I just said, we can't measure H. We can't know H final, we can't know H initial, so we're going to determine it another way. Okay, now let's look at this. For a chemical reaction, delta H is given by this. Products, how much enthalpy is in the products minus how much enthalpy is in the reactants. Again, we can't know the values of those, but that would be the true statement. So there is an H, we just can't measure it. There is an H final and there is an H initial. So I want us to examine here closely these two schematics that we see on the screen, on the PowerPoint. On the left-hand side, we see that we're starting off with a certain amount of internal energy of our reactants. Okay, these are our reactants. And it's going to our products down here. Okay? Now, for the products, it has less energy than the reactants, so we have to get rid of all that extra energy, and we see that it is given off to the surroundings. Now, if we're giving off energy to the surroundings, and there is a certain amount of H it has here, and a certain amount of H it has here, and this is the final, and this is the initial, then what would the sign of delta H be? Knowing that delta H is final, a little number, minus initial, a big number. Well, that would give me a negative value. And we use the term exothermic when we talk about processes that give heat to the surroundings, okay? Its enthalpy is changing. Final minus initial is getting smaller. On the right-hand side of the screen, these are my reactants. And this is the amount of enthalpy they have. I don't have a value measured for it, but I know it's down here somewhere. This is where it's starting off. These are my products, okay? So they have a certain amount of enthalpy that it's finishing off at. And we see that it's increasing the amount of enthalpy it has. So where is that energy coming from? It's coming from the surroundings. So we're putting in energy in order to get it up there. Now, if we do final, big number, minus initial, little number, then in this case we have a delta H that is greater than 0. This is our endothermic processes. So exothermic means it's giving off heat to the surroundings. Endothermic is absorbing heat from the surroundings, and this kind of goes hand in hand to our discussion that we had for Q. But delta H is a state function, Q is not a state function, but they are very much tied together. So what I'm going to have us do at this point is we're going to stop and we're going to watch a demo. It's called the thermite demo. It's a pretty cool demo. And once you've watched the demo, you're going to resume and you are going to choose one of these answers. So when I come back to you, you have watched the video, you've come back to here, you've chosen one of those as an explanation of what happened in the video. The demonstration you're about to see will be taking place outside, and you're going to see why here in a little bit, but it involves two substances.
One is iron oxide, which is basically rust in a powder form, and the other one is powdered aluminum. When these two substances are mixed together, we won't have anything happen until we light them. And we don't want to light it with a match or something that we have to approach closely to. So we have a secondary reaction, and this reaction will have glycerin and some potassium permanganate. As those substances are added together, it'll give a delay, which will allow Dr. Salt to back away from the reaction, and then smoke will billow out and the reaction will take place. And we'll talk more about the reaction after you get a chance to see it.
Okay, did you decide on what we have here in this thermite demonstration? Well, hopefully you said it's obviously an exothermic reaction. Surely you saw that it gave off a lot of heat. The amount of molten metal that landed in that sand bucket came from a lot of thermal energy. And if it's exothermic, then the delta H is going to be negative. Final minus initial, it gave off all that external energy to the surroundings, and therefore its internal energy decreased, the enthalpy decreased, and that's a negative value for that. Okay, there's going to be another demonstration that you're going to watch here. And this demonstration involves freezing a flask to a board, okay? So watch the video, choose one of these responses, and then resume.
This is a demonstration of an endothermic reaction. In an endothermic reaction, you have to supply heat in order to make the reaction progress. And sometimes you'd have to actually add a heat source, but this reaction can take enough heat from the surroundings to run, and so you feel it getting cold. We're going to attempt to freeze this flask to the board with a couple drops of water because it gets that cold. These are two dry chemicals that I will mix together. I have barium hydroxide and ammonium chloride, and it's kind of unusual to have two dry ingredients that will actually react well. When this reaction proceeds, it produces some ammonia gas, which I'll be able to smell. It also releases some water that was hydrated in the barium hydroxide, and it'll start getting a little slushy. When it gets slushy, I'm going to add the drops of water to the board and set the flask down, and then we'll wait a while. I'm going to add a couple drops of water. This flask has got an indentation on the bottom, so I want to try to freeze it on either side of the flask. And now we'll wait. So, if all works well, this flask, when I pick it up, will be frozen to the board.
Okay. Did you notice that the board froze? The water that was between the flask and the board, okay, was external, outside of it. But what did it do? It was an endothermic process. It pulled heat from the surroundings into the reaction. It pulled so much heat, it dropped the temperature of that water, and it froze it. And anytime you have an endothermic process, it's positive. Now, I still remember, I still remember being a student and really struggling with the sign convention of this. The reason delta H and delta H is positive for endothermic and negative for exothermic is because in order to give off heat, this system and the final minus initial, we're dropping the energy of that. It has to give off heat, and that's negative. It's really hard for me to hold on to that just as a memorized fact because it seems opposite of what I want it to be. But holding on, for the rest of general chemistry, not just this chapter, you need to hold on to the fact that if it's exothermic, it's negative delta H. If it's endothermic, it's a positive delta H. Okay, so what's the tie together between Q and delta H? This is the tie together. If you do a reaction and it is taking place in a constant pressure, underline the word pressure, constant pressure environment, then delta H, which is the enthalpy change, is synonymous with heat, is synonymous with Q. If you do the reaction under a constant volume environment, not a constant pressure, then all bets are off. They're not synonymous things. But Q, which is heat, and delta H, enthalpy change, are the same thing as long as you run that reaction as a constant pressure environment. That's really easy to do. As long as that reaction is open to the environment, the environmental pressure is pushing on it, the whole time the reaction is taking place, it's going to easily maintain a constant pressure environment. So this is a real convenient property to be constant because it's easy for us to undergo a constant pressure during the course of a reaction. So we were also going to talk about what are called thermochemical equations, okay? So what is a thermochemical equation? Well, it's a chemical equation plus something. You take your chemical equation and you give an enthalpy change for that reaction right along with that reaction. It says mass relationships because when we talk about stoichiometry, we can convert things between mass relationships. So it's given a balanced equation, but it's also giving an energy change. Here's an example. This is not a chemical process, it's a physical process. We're taking a solid H2O and turning it into liquid H2O. What's that process? We melted an ice cube, okay? If we had a mole of it and it underwent a process of melting, okay, the delta H would be 6.01 kilojoules. Now, would we say it releases or requires 6.01 kilojoules to melt that ice cube? Well, the value is positive, and that's endothermic. It's going to require. So to melt an ice cube, it has to absorb 6.01 kilojoules for every mole of water. Okay? So that's what it's saying there in the word form. In order to melt 1 mole of solid H2O, ice, and convert it to liquid H2O, water, you would require 6.01 kilojoules of heat. It would absorb that much. Okay, so there is a picture of that process taking place enthalpy-wise. On the left-hand side, we see enthalpy on the left. So we're starting off with H2O solid. It has a lower enthalpy. We're absorbing 6.01 kilojoules. In the process of doing that, it's breaking those intermolecular attractions between the ice cube crystals and turning it into liquid water that is a positive delta H. All right, now when we're dealing with thermochemical equations, there's a bunch of statements here that we need to keep in mind. So let's go through them. And this is a very important slide. Okay, so you need to know all of these things. First of all, when you're dealing with those coefficients, we must think about them in terms of moles. We can't think of them in terms of volumes, even if they were all gases. Can't do that. Can't determine them in terms of individual molecules. We always think about them in terms of moles. Okay? The next thing is, it says that if you reverse your equation, take your chemical equation and flip it over, it's going to change the sign of your delta H. Well, that should make sense. If we're going to take liquid water and turn it into a solid, this is the reverse process. So instead of requiring energy, it's going to release energy, and so we change the sign. But it's going to be exactly the same amount, just opposite in sign. So that's the second statement that we have to know. The third statement is if you change the coefficients of your balanced equation, notice here I doubled it. I doubled the amount we're dealing with. Well, if you double the amount of solid that you're turning to a liquid, you're doubling the amount of ice cube that you're melting. Should it not double how much energy required to do that? So anytime you multiply through on an equation, you also multiply through the delta H. Now, the last thing about the helpful hints here, it says that equations must specify the state. Obviously, this equation that we see on the screen would make no sense whatsoever without that and that. All right? Without that and that. None of those equations make sense without that, and that's going to be true for all thermochemical equations. We're going to see SLG for solid, liquid, and gas. We also might see AQ for aqueous. Those would be our common things that we would see after our substances, and you have to include those. There are a few other various ones that you might run across. You might see a GR, or they might spell it out all the way after a C. That means it's carbon in the form of graphite as opposed to carbon in the form of diamond. Okay? So you could see other things that are in parentheses after it, but typically solid, liquid, gas, AQ are what you'll see. So let's see if you can utilize the things that are on that helpful hint slide. If you look at the top equation, this is what happens in a Bunsen burner. This is what happens in a furnace if you have gas heat. Methane, which is natural gas, is reacting with oxygen to produce carbon dioxide and water. Balanced equation. It has a delta H for that balanced equation, which means that if 1 mole reacted with 2 moles of water, you would get those products, and you would also have the release of 890.4 kilojoules. Now, I want you to determine what delta H for this equation would be. See the equation? Look at it and compare it with the top equation. Once you've made the comparisons and seen how they're similar and how they're different, then you should be able to use the statements on the previous slide and determine which one of those is the correct value for the delta H of the bottom equation. Pause it, choose one, and then resume. Okay, did you pick D? If so, you're in great shape. But if you didn't, here are the common things that might happen. If you chose B, you flipped the equation. You recognize that it was reversed. And so you flipped the equation. That changed the sign. But you didn't go far enough. If you chose C, you doubled it. That was right, because you notice there's twice as much of everything, but you didn't notice that the reaction was flipped, and so the sign would be changed. So those are the manipulations that happen. You reverse the reaction, that changed the sign. You have twice as much there, so you're going to double the energy, and that gives you the answer for D, if you do those correct. Now, those manipulations are going to be very important for us as we continue on in this chapter. We're going to have to be able to do take a chemical equation, know it's delta H, do manipulations to it. We might cut it in half, we might double it, we might triple it, we will reverse it and change the sign, and utilizing that concept will be a tool in our tool belt of calculations that we'll have to be able to use. Okay, so that's going to end part 1, where we're defining enthalpy, we're looking at the sign convention of enthalpy, and we're looking at thermochemical equations.